Oh, great boy.
Okay.
When you see me, come on, baby, see like me like this. Hey, hey, all right. See the girl with the red dress on. She can do the bird that all night long. Yeah. What I say, all right. Well, everyone I say, everyone I say that now. Everyone I say, everyone I say that now.
Okay, time to get started. So welcome all. So I know I said I was going to take attendance starting today, but I ran out of time. I had, as y'all probably saw, technical difficulties. I couldn't get the thing to come up on the projector. That cost me 2 minutes of me trying to figure it out, 3 minutes of getting him to figure it out. And so we ran out of time. So I'm just going to not take attendance today after all. And we'll start on Monday, weather permitting. So, all right, so let's get back into the math. Let's see here. We already talked about, last time we talked about what a function is, right? Not that you haven't had lots of experience with functions, but very importantly, a function is a trio. It's these three things together. And a lot of people forget about the first two, but it is an important distinction. And we're going to kind of see some of why today. We talked about this example here last time. These two functions, they're both defined for all students at Duke. They both give the student ID number. What's the difference? Well, the difference is they have different targets. So these are technically different functions. Okay. All righty. Some more lingo that we have to define, and I'm going to try to be quick with this. And y'all may have seen some of this in a different context before. Like I say, I'm going to be kind of quick with it because it's mostly just lingo and it's stuff that you can kind of look at and think through somewhat on your own. So the word range gets used in this book and, probably more often than not this way, but it is used differently in other contexts. Range is the set of actual outputs that come out of the function. It's not the same as the target. You can see here, the target is Z, all integers, right? But not every ID, not every integer is an ID number. There are some 34-digit integers that are not ID numbers for any student. Right? Okay. So another example. Got a function here, real numbers in, real numbers out, defined by that formula. Note the trio, right? Domain, target, rule of assignment. Right? What actually comes out of this function? Well, just the non-negative numbers. Not every real number comes out. Right? So target and image are different things. And now a little side note, because this word gets used in different ways in different contexts, it makes me uncomfortable. So I tend to prefer to say image. You're going to hear me say image more often than range, but I will use range sometimes. Okay. All right. Now, if you look not at the entire function, but if you just look at a single example of a point going in and a point coming out, a number going in, number coming out, the output of that single story is called the image. It's the image of X. Okay. The input there is called a pre-image. And I think that lingo is pretty reasonable, right? Pretty relatable. The one it becomes before the image, right? So not too shocking. You will notice that this is A pre-image, there might be multiple inputs that give that same output. So you can't say it's the pre-image. We don't know it's unique. And in fact, sometimes you want to refer to the complete set of all pre-images. Sometimes that set is referred to as the pre-image. All right, so with that lingo done, I'm going to define these words. Again, you might have seen some of these before. You probably saw it as one-to-one and onto, but mathematicians tend to say injective, surjective, etc. But these boil down to a real simple idea. It's just a matter of counting how many pre-images the points in the target have. Okay, so let's start with onto, otherwise known as surjective. You need every point in the target to have at least one pre-image. So let's take a look at this. I've got some sort of abstract functions written down here. Let's take these one at a time. This is onto because every point in the target has at least one pre-image, right? Take this point right here, for example. It's got at least one pre-image. There it is. Right, let's take this point right here. It's got at least one pre-image. In fact, it has two pre-images, which is at least one. So cool. Okay, and you can see that not only is this function onto, but so is this one. Right? But you can see not, I want to do it like this, not this one. See, look at this target point. 0 pre-images. 0 is not at least one. Okay. So that's not onto, and this one here, likewise, not onto. Ready with me? Injective, very, very similar concept. Every point in the target has at most one. So this is the difference between one-to-one and onto. Surjective and injective, it's just at least one for every point in the target or at most one for every point in the target. And you will notice, for example, that this one right here, this is injective because that point has one pre-image, that has one pre-image, that has one pre-image, and that has 0 pre-images. And so altogether, every point has at most one pre-image. So it is one-to-one. This one over here also is one-to-one. This one's not, and that one's not. Okay, so it's lingo. Stuff's got to get said. It's just it's pretty standard in lots of mathematical contexts, and everybody just needs to see these words. By the way, this very convenient case of when you have both. Then we say it's an invertible function, otherwise known as bijective. Bi because it's both. Okay, it's got both of the objectives, right? So, okay. All right. So now this is actually kind of why we care about all this nonsense, because invertibility is important. We need to be able to invert functions, and a lot of people are a little too casual as to how they go about inverting functions. And so, for example, this function right here, domain, target, rule of assignment. A lot of people say, oh yeah, no, the way you undo a squaring is to take the square root. But you know, this function is not invertible. Right? This function is not surjective. You can't undo. How would you undo what this function does? How would you undo -3? How would you undo a squaring that results in -3? Well, nothing squares to -3. So the lack of surjectivity means that you can't invert. Side note, it's also not injective, right? How would you undo a squaring that gets to 25? You have two choices. There's kind of two different answers. Which one would be the inverse? Is it the +5 or the -5? It's not clear. Right? So very importantly, this function here is not invertible. So, however, if you restrict the domain, don't use all of R as your domain. Look just at the non-negative numbers. Restrict your target. Don't look at all of R. Look at just the non-negative numbers again. This function, domain, target, rule of assignment, same rule of assignment. Yeah, sure. But this has got a cleverly chosen domain and target that solves all the problems of the previous F function we were just looking at. And this is invertible. So this is what I like to call the invertible square function. The regular square function is not invertible. This is the invertible square function. Different domain, different target. And then because it's invertible, I can talk about its inverse. And its inverse is this function right here. It is literally exactly what you think it is. When you go into G, you square things. When you go backwards through G, you take the square root. Oh, and do notice, though, you will be taking the positive square root, because the domain of what we're inverting, aka the target of the inverse, is non-negatives only. Okay. All right. So formal treatment of something, old concept from long ago. But again, you can't play fast and loose with this because it doesn't work if you do. Now, here's another example I think you might be somewhat familiar with, but I'll bet you a lot of y'all are a little shaky on this point, and that is the same ideas applied to the sine function. If you just look at, y equals sine theta, that function's not invertible. But if you allow all real numbers in, all real numbers out, same problem. It's not invertible. It's not surjective. It's not injective. It's just a mess, right? But if you restrict the domain to just these angles, I'm drawing this on the unit circle. Okay, so these angles, if you want to look at it on sort of the more familiar graph picture, that's fine. But the unit circle is really kind of the better way to think about this. Restrict the target to just these values of y, which again on the unit circle is a little easier to look at. Then this is an invertible function. This correspondence that says you give me a theta, then pick the corresponding value of y by the sine. This correspondence, which just very nicely just looks like this on the unit circle picture. This correspondence is the invertible sine function. And its inverse is called arcsine. So, so this is why, a lot of people take the point of view of, oh yeah, when you take arcsine, you're only supposed to pick certain values. That's not a supposed. That's you're inverting something. What are you inverting? Side note, the thing you're inverting, it better be invertible. Right? And so arcsine is the inverse of this invertible function. And so it is, these values, let's see, let me highlight. We are picking these values of theta, because those are the domain of the function we're inverting. Everybody on board? Okay. Okay. Another little bit of lingo. So we're talking about multivariable functions now. Multivariable functions, multiple variables might go in. Multiple variables might be coming out. So here we've got m different output variables and in, oh, come on, stylus, in different input variables. Okay, and for whatever it's worth, the point of view, you can think of this as a bunch of numbers going in, but I would rather think about this as a vector going in. Don't think of this as a bunch of little things. Think of this as one big thing. It's a vector. So a vector goes in, a little bit easier to kind of see it when you write it like this. A vector goes in and a vector comes out. Or, depending on the context, maybe you think of this as a point in space, and it goes in and a point in space that comes out. Okay, so looking at these output values, depending on how many variables come out, depending on how many coordinates are in the output values, the vector values, we refer to such a function as, well, if there's only one coordinate, we call that a real valued or a scalar valued function. But if there are multiple variables coming out, then we call that a vector valued function. So just terminology. Analogously for in, switch the color, for in here, if there's only a single number that goes in, we call that a single variable function. So the terminology is a little bit different, appropriate to being a different concept. If multiple variables go in, we call this a multivariable function. So in other words, in some sense, you know, the real complications, and this is going to bear out as time goes on here, the real complication to taking derivatives and doing business, doing calculus with functions that aren't just, you know, Calc 1 kind of functions. The real problem is when you have multiple input variables. It's going to turn out having multiple output variables is really not that big a deal. It's you know, pretty straightforward matter. But having multiple input variables is where it gets weird. Yes.
I'm just clarifying for the bottom part. Should it
Yep.
be n greater than or equal to 1? Is there a difference, like, or should it be just greater than?
Oh, yes, thank you for catching that. It should be greater than. Yeah, sorry. Let me fix that. I will do that in red so that I can get that actually fixed. Greater than. Yeah, I spaced. Good catch. Greater than. Anybody else? Everybody on board? Another little bit of lingo here. The component functions, like let's look at y1 right there. So you can think of y1 as being one of the components of the outputs of this big function, or you could think of it by itself as actually, I mean, it's a function, right? Because within inputs, you get indeed one output. It is on its own a function. It's a real valued multivariable function. Okay. All righty. Okay. Last thing I want to say before we get into drawing pictures is that this is not some sort of abstruse discussion, philosophical. Does the fourth dimension really exist? That's absolutely not the right way to look at what we're doing here. Multivariable functions, vector valued even, they are everywhere. And so I like this example here. It's what I call the weather function. And by the way, this is a pretty tame version of the weather function. But you can think of it as that there's various things that determine, what the value of the weather will be. Where are you is part of it, right? But how high are you above ground level? Right, you go up 10,000 feet, it's colder up there, right? It's windier. And also depends on time, right? The weather 3 days ago was very different from the weather today. So there are very reasonably 4 different variables that we could call the inputs to such a function. And then furthermore, there's a lot of different outputs. We could consider temperature as part of the weather, and barometric pressure, and wind speed, and humidity, and probably a bunch of others that you could think of, right? Different ways to describe weather. So yeah, so what we have here then, notice, this is a vector valued multivariable function, 4-dimensional no less. Right, and yet this is not some abstruse ivory tower, mathematical weirdo only. No application to the real world. No, this is very, very relatable and natural. Okay, moving along. Okay, so how do we visualize functions? Graphs are what I'm going to start with, mostly because this is what you're most familiar with in terms of visualizing functions, because up to now, probably vast majority of functions that you've seen were single variable functions, where there's one number that goes in, one number that comes out. So real valued single variable functions. And that's just how single variable calculus is done, right? I mean, those are the pictures we draw. They're so ubiquitous in single variable calculus. A lot of people don't even realize that the graph of a function is not the same thing as the function itself. They're just almost universal. So here's the kind of picture. So the idea is you make a point whose coordinates give you both the input values and the output values. And you can see it right here, right? The input values, let's say they come first, not that they have to. The output values and come last. And I say familiar because, well, that's what we do when we look at, we look at y equals f of x, right? Well, the input x, we draw on the horizontal axis, the output y, we make that the vertical axis, and given an x, computing the corresponding y, and then drawing the point that has both as its coordinates is how you make a graph. Right, and so again, y'all been probably doing these kinds of pictures since, maybe since middle school. I don't know. It's a long time, right? So this is so ubiquitous. People think of this as that is the way to draw a function. It is important to recognize that this is not the, capital V way to draw a function. This is a way to draw a function, and it's a good one, and I like it. But it cannot be our only option. Okay, anyway, I'm getting ahead of myself. Let's see another example. Let's look at a multivariable version of a graph. Oh, question, yeah.
Yeah, so why is it a subset of R to the N plus N?
Oh, yeah. Great question. Okay, so she asks, what's going on here? So looking in general, you see our domain has in coordinates. Let me go back to the colors. Our domain has in coordinates, so there are in coordinates that come from the domain.
Why does it say less than R to the N? Like what is it?
Oh, this is a subset. So I'm saying, so my function might not be defined on all of Rn. It might just be a subset of Rn. Yeah. So we have, in some sense, in input variables and m output variables, and altogether, how many variables do we have? Well, we have altogether n plus m.
So R to the N plus M, does that just mean there's that many outputs?
This notation here says this is a list of ordered lists of coordinates, right? I was going to say doubles, ordered pairs, triples, but it's, whatever it is, right? Ordered lists that have that many coordinates. Yeah. Okay, so yeah, let's go back to the multivariable example here. Here we have a function from R2 to R1. The R2 are the inputs that we are going to make kind of the X and Y coordinates. We're going to make those kind of the horizontal coordinates in the picture we're drawing. The output value, I'm going to call it Z, also is a coordinate that goes into the graph. We're going to make that the vertical. And then all together then, the points that are on the graph is all these points where Z is equal to f of x, y, are points like this, right? And so I claim that this gives you a surface. And let's just kind of think that through. How is it that we know we get a surface? Well, for every point down here, why down here? Because that's our domain, right? Our domain is X and Y coordinates. So for every point down here, we're going to compute a Z coordinate by way of this formula. And that's going to tell us how far to go up from that point in the XY plane. And so in some sense, you can think of this as the function is telling you You start with a plane, you start with the XY plane, and the function tells you how much does that plane get lifted up. And it gets lifted up different amounts in different places, and it's going to make a surface. Everybody with me? So notice it's really just, it's a ripoff of what we did in single variable calculus. Same concept, just kind of, one extra input dimension. And so, one extra, all the bigger of a domain. Okay, let's see a function. Here we had a one-dimensional domain. Here we had a two-dimensional domain. What if we have a three-dimensional domain? Problem, right? Let's walk through that. Well, we have three input variables. Okie dokie. We have one output variable, whatever we want to call that. Let's call it W. And that means that points on this graph are going to be points with, we had three input variables and one output variables. They're going to be points with 4 coordinates. They're points in 4 dimensions. And I can't draw that, not even on a good day. Just forget about it. It's not really on the table. So the reason I like to show students this example is to emphasize that as much as we like graphs, right? We've been drawing these pictures for forever. These pictures allow us to see, in some sense, everything that's happening to the function. These pictures, we have so much familiarity with what calculus looks like, right? The slope, a geometric concept, is represented by something we know how to compute, this algebraic thing called the derivative. Concavity, this geometric concept of concavity. Yeah, we know how to compute that based on this algebraic thing called the second derivative. We know so much about graphs. We love graphs. Okay, they're not something that you can rely on because sometimes you just can't draw the picture. And if we were 17-dimensional mathematicians, it'd be a different story, right? But we have to recognize our human limitations, right? And we're going to have to think of some other way to look at pictures of certain kinds of functions. And I want to emphasize, I did not have to go to a lot of trouble to generate, the failure of the graph construction, right? A measly 3 input variables and graph is like out, right? So this is a problem. Okay. So so I've already kind of made this point, but I put a big box around it. So let me say it again. Don't conflate a graph of a function with the function itself. The function itself, we can write down functions for, we can write down all kinds of functions. That's a function, right? The picture that you use to represent it is, that's a separate thing, sometimes useful, sometimes really not. Okay. So what do we do with a function from R3 to R1? Well, so let me show you a totally different kind of picture. I like to call this the literal picture. I don't know. I've actually never seen a name for this, which is weird because these kinds of pictures have to get drawn all the time. I'm not making this up. This is a very standard way to represent a function. I like to call it the literal picture because, well, look, you've got a function where the let me do it better colors, where the domain is R3. Okay, there it is. I'm literally drawing the domain. The target is R1. Okay, there's R1. I'm literally drawing the target. And what does the function do? Well, the function takes things from the domain, spits out outputs in the target. It's literally doing something kind of like that. So this is not that creative. This is just kind of drawing what the function fundamentally is. It's as honest of a representation of the actual function as I can really think of. And notice it's not a graph. Right? The outputs and the inputs are not coordinates defining points. The outputs are way over here. Inputs are way over there. true to the reality, which of course is that they're totally different things. Those way over there are input points. This over here is an output. Why would you combine them into some, single thing? Doesn't really make sense if you really think about it. Okay, is everybody with me so far? So for this function here, if you're looking at a function from R3 to R1, if you had to choose between the graph and this literal picture, you take the literal picture because there is no graph. Okay. All right, now downside. Yeah, it doesn't show the whole function like the graph would. True. Disappointing. Can't help it. Right. It does give you something, right? You got to give me it is a picture. I can see something. I can see that this point goes to that point. And what we're eventually going to be doing is doing things like, all right, we're going to consider that, suppose I'm here and that thus having that as its output. Suppose I were to start moving that way at a certain velocity. How would the output value be changing? And see, again, I have a useful picture. Well, I at least have a representative picture that's showing my scenario of being at a certain point and moving at a certain velocity. And that's showing a representation of what I'm trying to understand, namely, what is the resulting velocity of the output? So this is nice. It's a good thing. And like I say, in any way, really better than the graph picture. Okay. Okie dokie. All right, here's another one. Level sets. Let's see here. Wrong mode. Level sets. Level sets pre-image. So in particular, if you have some function, and what you're going to do then is you're going to fix an output value, and then you're going to look at all of the inputs in the domain, that hit that output value, which is, again, the definition of a pre-image. Okay. All right, so a little bit of a disclaimer. While this is defined for any value of M, in other words, vector valued or not, whatever, that's all good. You can still make this definition. It tends to be most useful when that number is 1. In other words, when there's only a real valued output. So we're pretty much going to restrict our attention to real valued examples. Okay, so nice starter example. Here we have a innocent looking little function from R2 to R1. Yeah. Two variables in, 1 variable out. And let's draw some level sets. So keep in mind the idea of a level set is I fix an output value, and then I ask, what are the points that in the domain that hit this output value? Well, it's going to be the points for which x squared plus y squared is equal to 1. I want the points for which the value of the function is 1. So I'm going to just draw this as that circle, of course. And then now, likewise for other values, we could pick 2. What are the set of points that hit 2? Well, let's say, we recognize that algebra, and it's a slightly larger circle, and et cetera, right? I could go up to, I could go way over here to 4, and I would get a still slightly larger circle. Of course, the radius is the square root, right? But still, the further you go in the target, in some sense bigger, slower, but still bigger circles you get as level sets. Yes.
So is that a graph?
No, it's the level set. So thank you for the question. Y'all are going to have to start policing yourselves in your use of language. Okay, so when you say that word graph, you should flinch a little bit, right? And think, wait a second, am I actually doing this? And if you're not, then don't use the word graph. Right. So again, one of these things where every picture in a Calc 1 class is a graph. So the word graph and the word picture can kind of be used interchangeably. Yeah, whatever, who cares? Well, we at this point, they're not interchangeable. And again, excellent question. This is not a graph of a level set. That as a fact doesn't really even make any sense if you think about it. A graph is something you do to a function, right? This, a level set is a set. It's not a function. So these are just the level sets, period. These are the level sets. Yeah.
So, sorry.
No, it's good. It's good.
So this is a literal picture, right?
It's a picture. Yeah, sure.
Or like earlier you said it was a literal picture, but then.
Yep. Oh, well, it's not this, but yeah,
Oh,
but no. So the literal, what I call the literal picture, includes both the domain and the target and the little arrow representing the action of the function, right? But so this is just a picture in the domain. So the domain, if you want to do it this way, so R2 is the domain. This is the domain. So the level sets live inside of the domain. Yeah, but the level sets are level sets.
So isn't this whole thing a literal picture?
The-
Have the ring.
Oh, I'm sorry. Yes, no, yes, you're right. This is a literal picture of the function. Yeah, that's right. Yep. Sorry, I misunderstood your question.
So you said the level sets live inside of the domain.
Yep. Right, because here's the domain, right? That's the domain part of the function. And you can see these level sets, for example, this one, it is inside of, I mean, it's part of R2 there.
Okay.
Yep. Okay. Now here's one that's not very algebraic, but this is something that hopefully is relatable. If anyone's ever done any hiking and had a hiking sufficiently serious enough as to necessitate contour map, then you might recognize pictures like this. And what we have here, so the idea is these lines, that line right there is where the altitude is, I don't know, 100 feet. And then maybe this line here is where the altitude is 200 feet. And then maybe this line here is where the altitude is 300 feet, et cetera. And drawing lines like this allows you to kind of see that there's kind of a mountaintop there, perhaps, right? And so you can pretty useful if you think about it. You can even get some intuition for, well, do I want to hike? Let's suppose I were here. Do I want to go to the mountaintop by that path? Or do I want to go to the mountaintop by that path? And I guess it depends on what kind of adventurer you are and how hardcore, right? These days, I'm 100% going this way because look at this. I'm gaining, at worst, I'm gaining 100 feet over that distance. And that's not that bad, right? So that's not that steep. Whereas, man, if you go this purple route, you're gaining 100 feet. Boom, boom, boom. Oh my God, that's going to be super steep at the end. Nice and gentle at the beginning, sure, right? But brutal at the end. So that's a lot of valuable information. So it's a nice thing to have folded up in your pocket, right? In fact, notice these are level sets. So specifically, these are where you're setting the altitude equal to various different constants. That's what level sets are, right? So these are literally, contour lines are level sets of the altitude function. Does that make sense to everybody? Yes.
Can you explain again the rationale? So is it that the closer together the lines are, the steeper it is?
Yeah, because when you move from one line to the next line, you're gaining 100 feet of altitude. Now, would you rather gain that 100 feet of altitude over that much distance or over that much? You see what I mean? Does that make sense?
Yeah.
Yeah, sure. No worries. Okay. Okay, so yeah, so I like this example because it's kind of relatable. There's another example that is pretty relatable, I think. I don't know how much. It used to be that people would watch this thing called the news, which would have this thing called the weather segment. And then there'd be that guy standing there in front of the map, and they were all thought it was super cool because there's the map, and he would be pointing and stuff, but the map was behind him. And anyway, and so, but there would be a picture that would show temperature, and the picture would be something, kind of like this. And then there'd be, oh, whoops, hang on. I need to be in highlighter mode. There'd be kind of the red section down here. This is where it's super hot. And then there'd be an orange section where it's still pretty hot, but maybe not as hot. Maybe it goes over that way too. And then there'd be the warm, but still pretty nice section. And then there'd be the perfect and pleasant. Wouldn't it be nice if it was like that all the time? And then up here is where it's getting pretty cold, and maybe that's not so great. So you'd see pictures like this on the news. This old thing they used to do. So the nice thing I like to point out is these curves here between the different colored segments are level sets. They're level sets of the temperature function. And they wouldn't use those terms, but it'd be like, this is the, maybe this is the 60s, right? And this is the 70s, and this is the 80s, etc. Well, what that means is that this line, for example, that line is where temperature is 70. And that is a level set of the temperature function. So another highly relatable, well, in the olden days, picture, experience that is level sets. Okay. Next observation about level sets. They actually connect very closely to graphs. So let's look at this comparison right here. We're looking at a real valued function on R2. And graph, how do you make a graph? Well, the outputs are one of the variables on your picture. So said differently, you set the function equal to a variable. What's a level set? I should really color code this better. The graph is where you set the function equal to a variable. The level sets, level curves, if you prefer, are where you set the function equal to a constant. So if we can stop right there this is already an interesting comparison. Both graphs and level sets are what you get when you set the function equal to, well, different things, either a new variable or a constant. And so thus the difference, right? These are different constructions by that alone. The relationship between them, you can see when you think about what happens when you take a graph and you then take a horizontal cross section of that graph. Well, a horizontal cross section, it's a plane like this. And if you think about it, a horizontal cross, it's where you're setting z equal to a constant. And altogether then, a horizontal cross section of a graph versus a level set, they're really the same thing. In some sense, it's effectively f equals a constant in both cases. It's just that, it's f is a constant by way of this variable that's no longer allowed to be a variable. So therefore it's constant, right? Anybody with me? So we can see that bear out. This is the nice punchline. Level curves are horizontal cross sections of graphs. So here's the example. Got a function here, right? Not a very scary looking function, but anyway, there it is. And we can talk about its level sets. Reminder, level sets are what you get when you set the function equal to a constant. And we can look at these equations. They're circles. They look, kind of like that. Okay, now let's look at, let me color this that way. We're going to look now at the graph of this function. The graph is what you get when you set the function equal to a new variable, right? Because the points on the graph have to have both input and output variables. So those outputs have to have names. And okay, well, what is this thing? What do you get when you, what is this equation? X squared plus y squared is equal to z. I'm going to make an assertion here, and we'll see this bear out over time, but I'm going to then, anyway. It is a kind of a bowl looking thing, kind of like that. Here's the quick argument that I'm going to give to persuade you of this. I could rewrite this equation here as z equals r squared, and z equals r squared, that's an equation in cylindrical coordinates with no thetas in it, right? And as we talked about last time, if there's no thetas, then it's rotationally symmetric, and you can just look at a cross section. Okay, so I think it's easy pitch. So, okay, so we've got the graph, we've got the level sets, and now we want to confirm, are the cross sections equal to the level sets? Well, the cross sections are what you get when you take z and set it equal to a constant. So, for example, that, and notice this cross section is indeed a circle, namely it's a level set. And then likewise, here's a different cross section, setting z equal to a different constant, and you get still a circle, namely a level set. So this is just a bearing out of this rule that we wrote down, which is that level curves, level sets, however you want to say them, or are horizontal cross sections of graphs. How we doing? Okay. All righty. So let's see, this will probably be my last example today. Let's see how we're doing on time. Oh my gosh, we're so behind. We will catch up, it's fine. We now have several different kinds of, constructions, you might call them, several different ways to take a function and make a picture. We've got graphs, level sets, and don't forget parameterizations is another connection between functions and pictures. Right? So yeah, I claim it's very important not to confuse them, because ultimately knowing what function you're dealing with is, I mean, easily understood to be important, right? And if you look at the wrong function, you're going to get wrong answers, right? So in a situation where you need to know that this picture is the graph of something, if you look at the function that it's the level set of, then you're out of luck. So how do these functions look different? I'm going to look at this line right here, real simple equation. Whoops, straight line there. Oh, come on. Close enough. Okay, is this the graph of something? Well, yes, it is. This is the graph of that function, because if you set this function equal to z, then what you get is an equation that I think you can persuade yourself is equivalent to that equation, namely you get the same thing. So this function, its graph is that surface, that curve. Okay, now okay, that's not that bad, right? That's one of the arguments. But now let's think through. Okay, is this line a level set of anything? What is it? What function might I set equal to a constant to get that equation? And I think this is an easier one to see. It is a level set. Let's set it equal to a constant. let's set this equal to 6. Because that's what a level set. A level set, again, means you're setting equal to a constant. And sure enough, I get the exact same equation that I had there. So this line is also a level set. So yeah, it's a graph. Yeah, it's a level set. Very importantly, though, these are different functions, right? Can't emphasize that enough. This function and this function are not the same. So which one of these functions should you be doing calculus with? It depends. What in fact we're going to find out eventually, not even that long from now, is that there is what you might call a calculus of graphs. There are various kinds of derivatives we're going to be able to take, and there's various connections, various geometric interpretations that we'll make of what do those mean geometrically. There will also be a calculus of level sets, namely various different kinds of derivatives that I can take, and what do those mean when you're looking geometrically at a level set instead of a graph. So they're totally different. So which one of these functions you should look at, and by the way, let's throw into the mix, there's parameterizations as well, right? This line is parameterized by that function. We now have 3 totally different functions that all describe exactly the same line. Well, for this line, if there's something about that line that you would like to understand, and if the calculus of level sets would allow you to understand it, well, then you'd better use this function. Because it's the level set of that function and not that one and not that one. Okay. All right. And we are out of time, so we will draw a line right there. And although I did kind of, to be fair, I did already talk about the rest of that, but anyway, okay. Y'all have a good weekend. Good luck staying dry and warm and safe. Have a good one. Yep. I see it's a wrong page. 6. Okay. All right.